Go. There we go. They're described as being both one of my favorite chapters and the favorite of the students every time I've taught this class, because it's not super mathematical. It's sort of a puzzle game. It allows you to do some really cool things in terms of economizing experimental investigations. So what we're going to try to do today is carry that out a little bit further and show and get comfortable with the actual process that we kind of glossed over in the last lecture, actually, that dimensional analysis part of the process. So we sort of did this last time, but we'll get a little bit more practice with applying the Buckingham pi theorem to find the number of pi terms for a problem. Okay, and we introduced this idea of pi terms last time as being dimensionless variables that we can look at instead of all of the individual dimensional variables in a problem. We actually want to determine the pi terms using what we call the method of repeating variables. And then we're going to do a quick tour through some common dimensionless groups or pi terms that sort of exist and are well recognized and used all over the place. And you've probably encountered some of these before, especially those of you in BME, probably heard about Reynolds number, Weber number, things like this that are parameters, dimensionless numbers used to describe something about a flow. We're going to get into where those come from. So by the end of this lecture, you'll kind of, if you come across a Weber number, or a crude number, or a Mach number, step 2 here will sort of show you how the sausage is being made for those terms. So to quickly recap, right? In the last lecture, we proposed this problem that involved finding the pressure drop across a distance of pipe without knowing anything about the pipe beforehand. Or rather, being able to, taking a design specification for a pipe from engineers and being able to evaluate those designs in a completely different setting. For example, pumping water through a 1 meter diameter pipe with a mean velocity of 0.5 meter per second. How could we assess what the pressure drop and therefore the necessary pumping requirements are for that flow using flow through an air pipe like the one in the fluids lab downstairs? And one of the steps that we took here, right, is we said, we made the statement of the Buckingham pi theorem. Which says that, and this is I wrote it out in full form last time, this is the abbreviated version, that if you have some relationship between variables, and we'll use U to denote our dimensional variables here, 3, right, 4, etc., to U sub K, all right, where you don't have to know what this function is. You simply know that whatever U1 is, your dependent variable, it is somehow dependent upon each of the other 2 terms in here. So, for example, pressure drop unit length, velocity, diameter, fluid viscosity, fluid density was the example we gave last time. Then we said if you write out the dimensions of each of these U terms, if our U terms collectively contain R dimensions from our either mass, length, time, temperature, or if you prefer making things harder on yourself. The force, length, time, temperature, system of dimensions. Okay. Then we can rewrite this. We can capture everything important about this problem by writing pi 1, and this is a pi term, then is equal to some function of pi 2, pi 3, so on and so forth, to pi k minus r. In other words, if you find that your group of dimensions or your group of variables contains r dimensions, then you can reduce the number of variables by r, and each of these resulting pi terms will now be without any dimensions, meaning it's much more amenable to model scaling, testing at different sizes and by playing with combinations of fluid properties, size, flow speeds, etc. So this is the Buckingham pi theorem. Okay, this idea of taking a set of variables and reducing it down by r dimensions. The process of going from these u's to these pi's is what we're dealing with today. And it's accomplished through a series of steps that I've got outlined for you right here. And this is a set of slides that I will put up on icon, but we're also going to go through each of these in detail. So it's this 8-step process. The first is listing all the variables that are important to your problem. Okay? This is where you come up with that k count of variables. Things like density, velocity, as well as, right, one of these k needs to be the variable of interest, your output, your dependent variable. Step 2 is to write out the dimensions of each of these k variables. And this is where you're going to count up and say how many dimensions are there. That gives you your r. Step 3 is determining the number of pi terms using the Buckingham pi theorem, which I just gave you. And then we get into the new stuff. Step 4 is where you select what are called repeating variables. Okay? And you have to select r repeating variables. So if you have if you have mass and length and time in your dimensional set from step 2, then you have to pick 3 variables from your step 1 to be your repeating variables. And then step 5 is you take these repeating variables and you multiply them by the other, what are called non-repeating variables, with powers sufficient that you can cancel out the dimensions of those non-repeating variables. And you go through this and do it for each of these non-repeating variables. The step 7 and 8 are basically check that your results are actually dimensionless, and then ponder. So right now, this is probably not very. This is sort of a confusing list until you've seen it done at least once. So I've got first that we're going to practice this on the same problem we did last time. Okay, that we did in the last lecture, which was this flow through a pipe, finding the pressure drop per unit length. So we're going to be filling in that gap where before I just drew an arrow and wrote conventional analysis, yay. So step 1 is listing all of the important variables. This is where you come up with that count k. Right? So I've done this for us here, right? Idea, and we did this in class before, that if you've got your come on, there we go. That if we've got right, a length of pipe, and we want to determine, we've got P1, P2 at the other end here, and this pipe is some length L, that this delta PL, which is defined as P1 minus P2 over L, okay, is going to be a function of the diameter of the pipe, the density of the fluid flowing through it, the viscosity of the fluid flowing through it, and the mean velocity of the fluid flowing through it. The assumption here was that the pipe is smooth-walled. Okay, we're not going to deal with roughness. We will later, but for now we're going to leave that one out of it. So this is where we determine, right, and this is one of the, well, this is where we determine that value k. So we count it up. We have 1, 2, 3, 4, 5 variables for k. So we go ahead and write that down in the margin somewhere. K is equal to 5. Now, step 1 is we'll get some more practice with step 1 later, but this is probably the hardest and is almost certainly the most important of the steps in dimensional analysis. Because you're walking up to an unfamiliar problem and you just sort of have to pull out of your head what affects this problem. And so you've got to have some basic intuition, some understanding of what's going on, right? In a case like this, for example, if a person doesn't understand that fluid viscosity causes drag and therefore energy loss of the pipe, they may leave it out. Right? And in that case, you're going to be short one entire dimensionless group when you finish up the problem. And so you're not going to be capturing all the physics. So in general, it's better to err on the side of including everything. And then if you decide something isn't important later, you can always get rid of it. Some other things to consider. These variables that go in here have to be independent of one another. Okay. What I mean by this is that you cannot have any two variables that are related by some equation to one another. If I were to say that delta P sub L is equal to some function of diameter, rho, mu, v, the cross-sectional area of the pipe, the volumetric flow rate, and the kinematic viscosity. All right? They're all different variables, but we start to inspect these, you see, right? The area, we can get that from the diameter, right? So it's not independent. The flow rate, well, we can get that from the mean flow velocity and pi d squared over 4, right? So that's not independent. Kinematic viscosity is simply dynamic viscosity over rho, so that's not independent. So those are all superfluous. They shouldn't be included. We should cancel those out so that we have a set of k independent dimensional variables. All right. Step 2, then. And, oh, let me set this to be. All right. And we did do this last time as well, but express each of our variables in terms of the basic dimensions that make it up. So we've got, right, delta P sub L, we've got diameter, we've got viscosity, density, velocity, right? Here are our 5 dimensions, or our 5 variables. And we'll do these in mass length time and force length time, just so we have them both. The pressure drop per unit length, right? Well, if pressure is force per unit per unit area, and then that per unit length, what we'll get is force length to -3. Okay, and then we could also break that down into mass length to -2 time to the -2. Okay, so you've got to pick one of these systems of dimensions and stick with it. Which one you use is entirely up to you. You'll get the same results either way. Diameter, which of course has units of length in either system. Viscosity is going to be force time length to the -2. Shall be mass length -1 time to the -1. Density, right, is mass length to -3. So in force length time, that's going to be force length to 3 times squared length -1, I believe. So that'll be and then velocity is length times the -1 in either system. So the book doesn't try to steer you really one way or the other. I'm not going to be as diplomatic as the book. I much prefer working in the mass length time system. It makes most variables easier, and it's just familiar. So for examples in this class, we're going to stick with the mass length time, but you won't be penalized if you go with the force length time out of preference. So determining how many, like what our value of R is, right? How many variables comprise our set? If we look at either column here, we say we've got mass length, time, temperature. Okay. We can have a maximum of 4 variables. So mass length, time, temperature, force length, time, temperature, and how many actually appear. We've got mass, we've got length, we've got time. We've got force, we've got length, we've got time. In neither column do we see temperature here. So regardless of our choice, we've got R equal to a value of 3. Okay. Determining the number of pi terms. This is just, we're in 2nd grade math at this point. Right, we've got k equals 5, r equals 3, right? So k minus r tells us 2. We should have a total of 2 pi terms that we're looking for. Now things get a little bit tougher because now we're getting into the new stuff. In step 4, our task is to pick our repeating variables. Okay. Select a number of repeating variables where that number is equal to the number of reference dimensions. That means R. So if R equals to 3, or is equal to 3, we need to pick 3 of these as our special repeating variables. There are a couple of rules to go by here, right? Your set of variables have to themselves contain all R of your reference dimensions. Okay? So whatever our 3 variables that we pick have to contain mass, length, and time. Right? And they have to do so in a way that those sets of dimensions are independent. And we'll see what that means in a second. My recommendation for picking repeating variables is usually what's done is to pick those that are basically the simplest. If you've got ones that contain, like start out with those that represent a single dimension, pick one that represents 2 dimensions, and then another one that has 3 dimensions. And that guarantees that you'll be good in the sets that ensue. So for example, a single dimensional variable, diameter, right? That contains only length. Now, to pick, and let me write down these rules I sort of told you a moment ago. Rule number 1, repeating variables must contain R. The dimensions of our repeating variables must be independent. All right, what I mean by this is, since we pick diameter as one of our repeating variables, we can't pick any others that simply have length as a dimensional description. We have to have something that contains something besides length as well. So in a perfect world, if we had one that was simply length, another one that was simply mass, and another one that was simply time, we would just pick those three, and this process would be super easy. So we have one that has length. The next simplest is probably velocity, right? Because now it's length per unit time. So now we've got length, and we've got time involved, and those two variables are described by length and time in such a way that they have independent combinations of those dimensions. Length only for diameter, length and time for velocity. So the next one has to involve mass. And then we'll have satisfied both rules for picking repeating variables. The density and the viscosity both involve mass, right? This is mass, length, -3. Viscosity is mass, length, -1, time to -1. And this is where my urging to pick the simpler dimensions is going to push us towards density. Is our third repeating variable. So at this point, we've got 3 of them. That satisfies step 4. Okay, we have R repeating variables, D, rho, and V. They contain mass, length, and time between them, and they do so in such a way that no two variables can be combined to have the same dimensions as the third, which is really the formal statement of rule number 2. So now that we've got our repeating variables, okay, we've got rho, D, and V. The idea is that we want to be able to combine the repeating variables with each of the remaining non-repeating variables to form dimensionless groups. Non-repeating. Okay, we've got delta P sub L, and we've got viscosity. I'm going to quit writing in red because that's obnoxious. There we go. So let's make a little column, and this chapter is all about basically bookkeeping, organizing the way you arrange your work is going to make things easier. Let's quickly rewrite. Oh, I want black. Right. Come on. Rho, D, V, delta P sub L, mu. And I want to rewrite quickly the dimensions for each of these. Please still have them written down. Mass, length, -3, length times the -1. This guy was mass, length, -2 times the -2, mass, length, -1 times the -1. Let's move these over here. So we're going to go through this step twice. Once for this first non-repeating variable, and second for the second non-repeating variable. So take our non-repeating variable and write out delta P sub L, okay, times each of our repeating variables raised to a power. D to the B power times V to the C power. Yeah. Now, if we were to write out the dimensions of this resulting product, we would get then mass length -2 times to the -2, right, times mass to the A, length to -3A, length to the B, and length to C times to the -C. And if we want this thing to be dimensionless, right, the idea is we want the right-hand side to be mass to the 0, length to the 0, time to the 0. So this becomes an algebraic system of equations where we have to solve for A, B, and C to make that happen. We want this. So, write out your system of equations. We've got dA. You know what? Let's do it this way instead. Mass, length, time. 1, right, plus A going to be 0. Length is going to be -2 minus 3A plus B plus C equal to 0. And for time, we have -2 minus C equal to 0. Okay, can we solve for A, B, and C? Make that happen. Well, this one, clearly, A has to be equal to -1. Over here, C has to be equal to -2. Okay, just by inspection. And now if we plug those in over here, we'll find that B is to be equal to 1. Now plug those values back into our sort of our form of our first pi term, okay? And we'll get delta PL times D times rho V squared, okay? And this is defined as pi 1, okay? Our first dimension on the pi. And this should look familiar from Friday's lecture, where we said, here's one of those dimensionless groups. Okay. So we go through this process for each of the variables that's in our list of non-repeaters. All right. So if we do the same thing, do I have another sheet for step 5 here? No, I don't. Let me consolidate. Okay, we have that pi 2 will have to be equal to viscosity times rho to the A times D to the B times V to the C equal to mass length -1 times the -1. Now, mass to the A, length -3A, length to the B, to the C times to the -C. Mass, write out a system of equations, mass, length, time. For mass, now we've got 1 plus a, same as before, has to be equal to 0. For length, negative 1 minus 3a plus b plus c equal to 0. And for time, negative 1 minus c equal to 0. So a's got to be negative 1. Time has to be negative 1. And we will find in this case that length here is going to be did I have a mistake in my algebra? Hold on, I may have a mistake in the notes here. Nope, that's correct. C equal to negative 1. B is also equal to negative 1. So pi 2 is going to be equal to viscosity over rho v d. All right. Those of you that recall Friday's lecture might see that this appears to be inverted. In Friday's lecture, we proposed one of our groups being rho v d over mu. This is one of the things with dimensional analysis, is we can use either a dimensional group or we can manipulate it by taking its reciprocal. If you do rho v d over mu, then that's a predefined dimensionless variable called the Reynolds number. So it's more familiar, more standardized. And so we tend to do that instead of this form that we derived. There was another slide for step 6. So step 6 should have been that second non-repeating variable. And then step 7 and 8 are checking our work. So we did this in the previous lecture. We'll skip this for the sake of time now. But we know that pi 1 ends up giving us, mass 0, length 0 times 0. That pi 2 gives us the same. And so our new expression becomes, that delta p sub L times d over rho v squared is equal to some function of mu over rho v d. And here's where we say if it's a function of this number, then it is also going to be a function of that number's reciprocal. So we often just replace with rho v d over mu, so that we've got a more familiar variable in place. And now we pick up where we sort of left, or we leave off now where we picked up on Friday. So having the quiz really puts a damper on being able to do another example. Tell you what, I've got another example. Doing this, we'll do the first thing on Wednesday. Yeah.
What happened to pi 1?
Pi 1? This is pi 1.
Oh.
Good. Pi 1, pi 2. Note, I got this question last time. The pi really doesn't, honestly, I have no idea why they chose pi. It's just a symbol here, capital pi, that they're using to represent dimensionless groups. It has nothing to do with 3.14, etc. Okay, so don't make the mistake of confusing it with the numerical constant pi. So what we'll do quickly here then is I'll just mention, so I said there are these sort of pre-existing standard pi terms that are out there, okay? And these are what are known as, these are common dimensionless groups. So I just mentioned this one. Hold on. There we go. So the Reynolds number, for example, is the one we just derived. Density times velocity times some length. Okay, and that length can be a diameter, it can be the length of a plate, etc. And we'll see later as well that this can basically be interpreted as the ratio of inertial forces to viscous forces, and makes the difference between what we call laminar and turbulent flows. Okay. There's the Froude number, which is really common in anytime you have a fluid-free surface, especially one that has waves. So it's very near and dear to people that work in ocean and lake environments. And this, because it's a balance between inertial forces and gravitational forces, this is basically the dimensionless constant that captures the physics underpinning waves. The Euler number is another one that we get to later. This is defined as the pressure at a point over rho v squared. And there's a special form of this called the cavitation number that is the difference, okay, the pressure up there is replaced with a pressure difference between the pressure at some point in the flow and the vapor pressure of a fluid, okay, divided by 1/2 rho v squared. And so the way this is defined, the reason it's called the cavitation number, is because when this is equal to 0, you're at the vapor pressure. And there's other ways of basically, I'll leave this till later, but you can set a threshold and say if the cavitation number falls below this point, then places where the pressure coefficient is equal to such and such, you'll get cavitation. There's the Mach number, which is defined as the speed of a flow over the acoustic speed in that flow, or the speed of sound. The Struhel number is defined as the frequency of some occurrence times a length scale over the velocity. And this is what underpins this process that we call von Karman vortex shedding. Basically, this idea that when you've got a bridge piling or some other blunt object that flow past it, you'll get these alternating vortices that get shed off of it. And it turns out that if you count the frequency of those vortices, you take the length to be the distance between them, and you measure the velocity of the speed, the Struhel number there will always be the same. Okay, it's generally around 0.25, regardless of how big the piling is, how fast the flow is going, etc. And it looks like we're out of time. I think that's the last of the dimensionless groups. We'll pick up with more examples on Wednesday.